Hello everyone, welcome to this next video on complex analysis. This video is taken from the paper GATE 2000 and here we have a question of 2 marks. The question says for the given function f of z defined to be 1 minus e to the power minus z divided by z at the point z is equal to 0 is an essential singularity, a pole of order 1, pole of order 0 or a removable singularity. So here we have a lot of confusion how to check these kind of singularities. For that I have illustrated 2 methods that I shall be discussing in this video. So let us have a look at the first method first. So it says if we are to find any isolated singularities, so what we can do, we can expand the function in terms of its Laurent series expansion, and I have already discussed it. So it is something like this. It have the analytical part and the principal part. So and the coefficients here are calculated using this particular formula. So this is the definition for Laurent series. Now in order to calculate the singularities, we say when the degree of principal part is 0, then we have removable singularity. So that means if the degree of principal part is 0, so let us have a look. So that means we do not have any of these kind of terms present. So that means z minus the point of singularity, that should not be present in the denominator, right? So if that is the case, then we say it has a removable singularity. For example, for this function sin z by z, we can expand this sin z function into the series form and we can have we obtain this thing. So here we see that there is no term of z that appears in the denominator. So here we can say it has a removable singularity. For pole, if we have the degree of principal part as some finite number, that means we have some finite number of terms of z which appear in the denominator. So that means in principal part we have certain finite number of terms present in it. For example, we have this function sin z divided by z square. So when you again expand it into the series form, so you will have something like this. So here you see this term is present where this z is appearing in the denominator part. So we say, and such terms having the presence of z in the denominator corresponds to pole. So we only have one term of such kind. So we say we have a pole of order 1 because of the presence of this particular term. And for essential singularity, the degree of principal part should be infinite. So here, for example, we have the sin 1 by z, so we can expand it using this expansion, right? Here you just have to replace the z by 1 by z and you will obtain this particular series. So now you see here the terms 1 by z, 1 by z cube, 1 by z raised to power 5 and so on, they goes to infinity. So here the degree of principal part is not defined. So we have essential singularity for such cases. So this is one method where we can use the Laurent series expansion, but here this method is not applicable every time. So what we can do, for example, in some functions, say z is equal to a is a point of 0 as well as a singularity. For example, in this case, if we have a function sin pi z by z minus 1, so here z is equal to 1 is a simple pole, because when you substitute z is equal to 1 into this, you have your function approaching to infinity as z approaches to 1. So therefore we have a simple pole at the point z is equal to 1. Wherever you see, if you substitute z is equal to 1 in the numerator, you have the value as 0. So that means z is equal to 1 is also a root of sine of pi of z. So if we share a common root as well as a singularity, so in that case what you can do, you can just check this particular limit. The limit of the function when z goes to that particular point where you have this kind of ambiguity. So if this limit comes out to be a finite number, you can directly say we have a removable singularity. Otherwise, if this limit is infinite, so you will say we have a pole at that particular point, z is equal to a. So let us now move back to our question. So they were asking about this particular function f of z, that is 1 minus e to the power minus z divided by z. So we can expand this e to the power minus z into the series form. So we would have 1 minus z plus z square by 2 factorial minus z cube by 3 factorial plus so on, right? So we can use this particular series and we can substitute it over here. So let us see what do we obtain. We have f of z, that is equal to 1 minus of this particular series, 1 minus z plus z square by 2 factorial and so on, minus so on, right, divided by 1 by z. So here you see this 1 and 1 cancels and this z and z cancel, so we would have in effect 1 minus z by 2 factorial plus z square by 3 factorial minus z cube by 4 factorial and so on, right? So this is our function. So now here we see there is no term present in the principal part. All the z terms, they are present in the numerator itself. So that means we can claim from here that we have a removable singularity for this particular removable singularity, right, for this particular function. Moreover, we are to check at the point z is equal to 0, and to be on the safe side, let us evaluate its limit. So let us evaluate this limit. Z goes to 0 because we are given this point z is equal to 0 of f of z. And what is f of z? 1 minus e to the power minus z divided by z. So here if you substitute z is equal to 0, you will end up by 0 form, right? So here we have to differentiate in order to calculate this limit, and we are to apply L'Hopital rule, right? So we have to differentiate the numerator separately. So if we differentiate the numerator, we'll be having minus e to the power minus z, and if we differentiate the denominator separately, we would have 1. So now if you substitute z is equal to 1 here, you have 1 as the answer, which is a finite number. So now we have a finite number, so that means we can clearly say we have a removable singularity at the point z is equal to 0. So here option D is the correct option. So I hope you understood this question and concept well. I'll see you in the next video. Thank you for watching.